I'm absolutely delighted to be back at the IVAM workshop here in RAK, and I thank Professor Cheetham for the invitation, and also Natalie and the IVAM team for all the logistic and arrangements. So I think my talk will give an idea about the scientific impact of the wonder materials that Andre talked about, some new ideas developed here. So I'll be telling you about new vibrational spectroscopies that we propose, which are based on quantum geometry of electrons. The work was done by my PhD student, Bhuvaneshwari, and we collaborated with an experimentalist, Mandar Deshmukh from TIFR Mumbai. Work is supported by the Department of Science and Technology. So you have seen first principles calculations used very commonly in different aspects of material science. These days it's very fashionable to design new materials starting from scratch using first principles calculations. In this talk, you will see that we can even formulate a new experimental technique starting from first principles calculation. So in that sense, it's a really new way of doing science. So it's a new class of spectroscopies which are based on quantum geometry, and we will demonstrate it in the 2D materials, a subset of what Andre talked about, and demonstration is for the vibrational spectroscopy. So it also marks 100 plus 1 year of Raman effect, and what you will hear in this talk is essentially a new type of Raman effect, but which originates from quantum geometry. So you may have seen this picture in popular science magazines or news media, where light emanated by a distant object in the universe can go past another star, bend its trajectory to reach Earth. This is called as gravitational lensing. And this doesn't happen because this heavy object is attracting light photon gravitationally, but it is because the space-time through which light passes is curved. The question we ask is, can this be seen for electronic trajectory? And the answer is yes. It is related to the curvature of quantum phase space in which electrons move. So you can find similar effects in a desktop experiments, including, for example, graphene-based systems where such effects can be observed. So since I saw that in the poster session, most of the students here are from chemistry background, I'm going to take a little time to tell about what quantum geometry of electrons is and what we mean by that. So it's a brief introduction to that. So all of you know that electrons in a crystal, which is a periodic system, are subjected to a potential, which is shown here, which has a periodicity of the lattice. So you will expect electronic wave functions to be also sort of periodic, arising from atomic orbitals, but many of you know that the Bloch's theorem gives you that this periodic part of the wave function is modulated by another sort of sinusoidal wave, which is called as a plane wave. So that's the Bloch's theorem. This is Bloch function of an electron in a periodic crystal. Okay, and you usually see band structure, which is seen by catalyst, people working in catalyst, where energy versus Bloch vector is usually visualized. Okay, so what to remember from here is the Bloch vector, k vector, is a continuous quantum number that labels electronic states in a crystal. Okay, all right. And the crystal momentum of an electron is proportional to this Bloch vector k multiplied by the Planck's constant. So periodicity of electrons in a crystal is more than what you saw on the last slide. The periodicity is also there in reciprocal space. For example, the wave function at k plus 2 pi by a, which is the periodicity of the reciprocal space lattice, is identical to wave function at k. Yeah? As a result, you know that this particular electronic state is identical to this state, which is displaced by a reciprocal space lattice vector, and so on and so forth. So this periodicity in reciprocal space is also for energy as well as wave functions. So what happens, usually you will visualize electronic structure only in one small unit of the reciprocal space called as Brillouin zone, which runs from basically minus half of the unit cell to plus half of the unit cell. It's called Brillouin zone. So how does electron move in a crystal? As I told you, block vector gives you momentum. So when one applies force to an electron, say electrical field force, the momentum will change. And the trajectory of an electron in the quantum phase space will be given by displacements from k to k plus delta k. Okay? So if it's a Brillouin zone shown here in two-dimensional space, electronic trajectory will be given by this red dashed line if the field is along x direction, or by the blue dashed line if the field is along y direction, and so on and so forth. But if you now remember that wave function at this point is identical to wave function here, or here and here, then this periodicity says that this dashed line is actually a closed path on a toroid, which is representing the Brillouin zone. So when an electron traverses from one end of the Brillouin zone to another end of the Brillouin zone, the electron is gone along a closed trajectory. Yeah, that's the closed orbit. So whenever an electron or particle goes along a closed orbit, there is an emergence of what is called as geometric phase. And I'll take 1 minute to give this demonstration. So imagine that electron is represented by a wave function in quantum physics, where you can think of it as a vector in a Hilbert space. So imagine that this is p orbital of an electron. I'm holding it with my arm, and I move my arm by maintaining the angle of this orbital with respect to my arm to up, take it to the 9 o'clock position, and bring it back. What happens is the orbital or the vector has rotated by 90 degrees. And this angle depends entirely on the solid angle that is subtended by the closed trajectory, closed loop that I showed. Yeah? And that's why it's called as geometric phase. In fact, geometric phase was first imagined by Pancharatnam in Bangalore in 1950s in the context of optics, and later by Joshua Zach in the context of block electrons, and then Michael Berry in 1984, which is 50 years after the quantum mechanics was developed, 60 years. This was realized in quantum physics, and since then it has been everywhere in quantum phenomena that you come across. So this is to tell you what we mean by quantum geometric phase of a quantum electron. Okay, so that you will see will be useful in defining quantum curvature of an electron. So there's one more result I wish to share with you. This was a very beautiful result, which was shown by David Vanderbilt and Dominic Kingsmith, who showed that the geometric phase of a block electron actually gives you average position in real space of an electron. Okay? So this is slightly complicated looking formula, but it's very easy to understand. On the left-hand side is the geometric phase, and on the right-hand side is the average position of electron in real space. Now, this alpha basically is a label for x, y, z coordinate, and this integrand is called as Berry connection, which is a vector quantity in 2 or 3-dimensional spaces. So this tells you how electron goes from k, the wave function changes with respect to the parameter k, and overlaps with the next wave function, and then if you integrate it along a closed loop, minus pi by a to pi by a, you get a geometric phase. But the key point is it tells you average position of electron in that direction. And that will be crucial to sort of go to the next stage. Okay, so in 2 dimensions, you imagine you have 2 types of trajectories, one which runs along x direction, one running along y direction, and the Berry phase along this gives you average y position of an electron. And if Berry curvature, Berry potential or connection is given by a vector, the Berry phase is given by this loop integral, and Berry curvature is a curl of this Berry connection in reciprocal space. Okay? So let's imagine what happens if the electron is moving along x direction and Berry curvature is non-zero. This is the key quantity I want you to understand. If omega is non-zero, an electron goes from k to k plus delta k x along x direction, its y position can change. Right? If the Berry curvature is non-zero, electron moving along x direction also changes its average position along y direction. That's the key sort of idea, physical interpretation I wish you to remember. And what that means is applied electric field
will push an electron along x direction, but will also cause change in the momentum along kx, as well as the change in the position along y, which generates a velocity along transverse direction, y direction. And this is called as anomalous velocity because there is no force acting in y direction which causes it. It is arising essentially from the quantum curvature of electronic structure. Okay, so as electron moves along x direction, it's also shifting along y direction, changing its y position, and omega, which is called Berry curvature, acts like a magnetic field, which is causing a Lorentz force and moving electron in a y direction. So what was shown long ago by Karl plus Lettinger is that if you have a two-dimensional system with an electron gas which is enclosed in this Fermi surface, the closed loop integral of the Berry phase, phi, actually gives you the off-diagonal conductivity, sigma xy. What it means is if the field is applied along x direction, it generates electric current along y direction. And this happens in the absence of any external magnetic field. And that's why it's called anomalous Hall effect, that Ex causes Jy, and the origin of this sigma xy, the proportionality comes from the geometric structure of quantum electron. Okay, so this is the background. And these are ideas which are very powerful and general. So here is an analogy between the electromagnetic fields which emerge from the geometric structure of quantum electrons and electromagnetism that you are familiar with. The Pancharatnam geometric phase is actually the Arano-Baum phase. Berry connection is like a vector potential in classical electromagnetism. Berry curvature is the magnetic field strength, and the Chern number, which is defined for an insulating system which has a gap, which is integral over the whole Brillouin zone, is the topological invariant of electronic structure, and that corresponds to like Dirac monopole charge in the which doesn't exist in classical electromagnetism. As a result, you can have really interesting phenomena that emerge from the quantum geometry of electrons. Okay, so take-home message is Berry curvature is crucial. It's like a curvature of quantum phase space of electron, and I showed you how it gives rise to anomalous Hall effect. And topological insulators, which also came up from 2005, are indeed linked to this Chern number that I have defined here. And I won't go into that. That's a separate topic. But indeed, these ideas are also relevant to defining topological insulators or also Weil semimetals. OK, let's move on. These ideas are all very nice. But unfortunately, symmetries are quite restrictive. The Berry curvature is an odd function of k, reciprocal space vector, due to time reversal symmetry. And it also is an even function of k because of inversion symmetry. So many materials like silicon, aluminum, which have both of these symmetries, will have Berry curvature, which is identically 0. All that means is electrons in these systems are moving in a flat space of quantum numbers. Okay? And none of these effects that I described will be observable in them. Well, there was something called nonlinear Hall effect, which was proposed based on Berry curvature dipole, which is less restricted by symmetry, and that's what attracted our attention. So even if you have time reversal symmetry, if you break time reversal symmetry, you can have non-zero Berry curvature. But if you have applied electric field to the system, you will break inversion symmetry due to application of field. As a result, the Fermi surface will shift along the direction of electric field, which creates an asymmetry in the occupation number. There are unoccupied states here and extra occupied states. And this asymmetry can give rise to what is called as Berry curvature dipole, which is the first moment of Berry curvature in reciprocal space. And based on this Berry curvature dipole, there was a theoretical prediction by Liang Fu and Inte Sodeman, who showed that indeed it gives rise to second-order nonlinear Hall current in the absence of any magnetic field. In this case, the transverse current, Hall current, is proportional to square of electric field along x direction, and the proportionality constant is given by Berry curvature dipole. And because it's a second-order effect, even if you apply electric field along x direction, which is AC field at a frequency omega, it will generate rectification signal or second harmonic generation in the Hall signal, transverse direction. Okay, so this was theoretical prediction, and just for the theory students here, the Berry curvature dipole, as you will see, is the first derivative or first moment of Berry curvature in K-space. Okay, so how does this relate to experimental observations? On the left, I'm showing you the linear anomalous Hall effect in systems where you have non-zero Berry curvature. This is sort of the electronic band structure, and blue color tells you that Berry curvature is same everywhere, same sign everywhere. And if that's the case for applied electric current along x direction, there will be anomalous Hall effect, which will generate current along y direction, but the effective current will be at the same frequency, and as a result, due to vector addition, it will be at a small angle with respect to the applied field. On the other hand, nonlinear effect, although it's weaker in magnitude because it's second order, it is at a frequency which is different from the frequency applied along x direction. So as a result, this signal is always perpendicular to the applied field and little easier to measure. It will have both zero frequency, like rectification, and 2-second harmonic generation. And indeed, this was observed experimentally in a system which also involved boron nitride and a few layer graphene. This was observed by Pablo Herrera's group at MIT, and also it involved a tungsten telluride, which is non-centrosymmetric. So this is a calculation from our group, which shows visual picture why this effect arises in tungsten telluride. Basically, this is the Brillouin zone, and this is Berry curvature distribution. You will see it has a polarity in K-space. And these are things you can readily calculate from density functional theory calculations. So this non-zero Berry curvature dipole is what is responsible to nonlinear Hall effect. Okay. So in one of our works with Mandar Deshmukh's group, this was experimental work. What we showed is in a system based on graphene, these ideas can be quite interesting as well, particularly what is called as a Moire superlattice, which is a twisted version of graphene. Mandar's group looked at twisted bilayer graphene, where two bilayers are twisted with respect to each other by an angle theta, about 1 degree. This is the experimental device geometry that he had. This is the channel, and there are electrodes which are gate as well as there's top gate electrode, bottom gate electrode, and other measuring electrodes. And with this geometry, the experimental group can control both carrier concentration in this channel as well as the perpendicular electric field which is applied to the channel. Yeah, that's given by the difference between the two gate electrode voltages. And this way they have control over electronic structure, they can tune electronic structure, and what can be shown is that the Chern number, which I defined earlier in this talk, for K valley and minus K valley, you see they are equal and opposite due to the symmetry of this graphene. And it basically changes if you apply the perpendicular electric field from a minus to plus sign. And this is a kind of topological electronic transition, which involves reversal of Chern number as you apply its valley Chern number in this case. And that could be tuned by applying perpendicular electric field. And what we showed is this change in the topological invariant, topological transition can be detected using Berry curvature dipole. And in other words, if you do nonlinear Hall measurements, you can detect this phase transition in a nice way. And this was experimental result which we explained that for one filling, you will see a positive slope to the second harmonic generation, and for the opposite Chern number, it is negative. Yeah? So this way, one can easily detect a topological transition using nonlinear Hall measurements, which are based on Berry curvature dipole, and that was sort of the experimental work that we got into. At this stage, my student was very creative, and she said, well, as you will see, that Berry curvature dipole effects also are highly restricted by symmetry. You need low symmetry crystals for that. And more importantly, you also need small band gap, narrow band gap materials. And that's also very restrictive, because Berry curvature is large if the band gap is small. What do we do to see it more generally? So our idea was we can lower the crystal symmetry dynamically, right? For example, in a vibrational mode, the symmetry of a lattice can change as a function of time. And this is the basic idea in this new experimental tool that we propose. This is hexagonal structure, for instance, graphene. And if you freeze in a vibrational mode, shown by these arrows of the two sublattices, if you look at an instantaneous snapshot of the structure during vibration, it lowers the symmetry of the lattice, and here Berry curvature dipole can be non-zero. Yeah? So vibrational mode can induce Berry curvature dipole in a system. And that was the key. And based on that, we said, well, there should be oscillations in the nonlinear Hall signal, and that, based on that, we proposed a new spectroscopy. If you measure oscillations in nonlinear Hall signal, you will be able to tell the vibrational frequency of the system. So that's the new spectroscopy that we propose. So the idea is the crystal symmetry is lowered by dynamical oscillation of the lattice, in this case vibration, and if the amplitude of vibration is u, it induces oscillating Berry curvature dipole with a period given by the vibrational frequency. And the frequency-dependent nonlinear Hall current has two components. First one was what was given by Liang, Fu, and Siedemann, which is the normal second harmonic and rectification signal, whereas our work shows that you will have additional peaks in the nonlinear Hall effect, which are related to the vibrational frequency and the modulation in vibrational frequency with plus minus applied electric field frequency. Okay, so, and the selection rule is basically Berry curvature dipole should change linearly with the vibrational amplitude. So that's the selection rule. So based on that, we first propose a transport spectroscopy, where you have a channel of your material shown here, and there are two electrodes which apply driving field with a frequency omega AC, and one measures Hall current in the transverse direction. And you will see this is our sort of prediction based on the theoretical analysis, that you will see 3 peaks as a function of frequency. One will be centered at the vibrational frequency associated with rectification. And there will be 2 Stokes and anti-Stokes-like peaks, but they are separated by 2 times applied frequency, omega AC. Yeah? So if you measure this Hall response, one should be able to tell the vibrational frequency, and these 2 peaks will give you additional handle over detecting vibrational frequency omega naught. Yeah? So indeed, this is an example where you can use electrical circuit to measure vibrational frequency of the channel. Yeah? That's a spectroscopy. That's why we call it transport spectroscopy. The second is emission spectroscopy, where you can also imagine light shining on the channel, and then you measure emitted light with a perpendicularly polarized electric field, and the spectrum of that emitted light will also have a structure as shown here. For inversion asymmetric, non-centrosymmetric structure, you will have rectification and 2 times the light frequency, but also due to the vibrational modulation, you will have additional peaks here which allow you to measure vibrational frequency of the system. So these are 2 scenarios in which the GQS spectroscopy can be implemented. One is transport and one is emission. So until now, it was all a sort of analysis. Now we use first principles calculation to demonstrate that indeed in some real systems, this will be observable feature. So we start with the material which was studied by Pablo Herrera's group, namely non-centrosymmetric tungsten telluride. And if you oscillate this using this strain mode, as I have shown, that mode, vibrational mode, actually corresponds to longitudinal acoustic phonon, the vibrational frequency. And it's fairly low frequency mode. And if you look at the electronic structure, the bands will oscillate with respect to this strain 1% and -1%. Indeed, this is to tell you that knowing band structure does not tell you if anything is changing in the quantum geometry of electrons. To know quantum geometry, you have to calculate Berry curvature or Berry curvature dipole, and we explicitly show that it's linearly proportional to the strain that you freeze in the lattice, and as a result, you will see peaks in the Hall signal at basically omega naught and these additional peaks. So this is what is our specific prediction for tungsten telluride. You have a channel, you apply electric field with a frequency omega AC, and measure Hall signal as a function of frequency. And the prediction clearly shows that, in fact, there will be 2 side peaks associated with this applied frequency, and using them, you can easily tell what the vibrational frequency is. Yeah? So this is a specific prediction I think should be observable. Next is where you will consider centrosymmetric structure, where you don't have any Berry curvature or Berry curvature dipole. But even in this system, we show that using longitudinal as well as optical phonons, one can induce Berry curvature dipole, which is linearly proportional to vibrational amplitude, which means both of these phonons are active in the Gequest spectroscopy that we proposed here. And as a result, we show that we predict that vibrational spectrum should be measurable if one measures Hall voltage or Hall emission from this sample. And this is how it looks. These are the two Stokes and anti-Stokes peaks come out. And this is the terahertz frequency where it was the applied frequencies there. Yeah, so these peaks very clearly will identify vibrational modes of the lattice. Okay, so this possibility opens up a technology that if you have frequency modulation in gigahertz, you can transfuse it to the terahertz frequency range. And that's also a very important tool because there are very few sources and detectors in terahertz frequency range, and this technique allows you to go from gigahertz to terahertz frequency range. Okay, so our idea about dynamical lowering of symmetry works, but unfortunately, these ideas appear to be still very restrictive. So because narrow band gap and low symmetry structure. So we overcome this now by saying we can use graphene as a substrate, which is a quantum material, which can have non-trivial quantum curvature. And we want to measure vibrational frequency of hexagonal boron nitride, which is a large band gap semiconductor with very boring quantum geometry, flat space. So if you interface boron nitride on graphene, you will see that vibrational mode of boron nitride also induces the oscillations in electronic structure of graphene and also gives rise to Berry curvature dipole, which is linearly proportional to vibrations of hexagonal boron nitride. So this is our proposed experimental measurement. You have hexagonal boron nitride, which will have a macroscopic oscillation or the optical mode oscillation, and which is deposited on graphene, and you measure Hall emission from that. You will see the peak structure will have vibrational frequency at the center, and two side peaks, which will be related to the frequency of light that you use to probe this signal. Yeah? So indeed, you will use now graphene as a substrate. It's like a surface-enhanced Raman scattering, but in this case, graphene is the active quantum material, which allows you to measure vibrations in boron nitride. This is how it looks like. This is the vibration of HBN. You will see oscillations in HBN. And as a result, the frequency-dependent Hall signal will be measuring for you the vibrational mode as well as modulation with respect to the applied voltage or the applied frequency of light. Okay, so indeed you can calculate the full spectrum of non-centrosymmetric tungsten telluride, and I won't go into these details, but the news is it's a fairly rich spectrum and should be observable in either using circuit or using emission mode spectroscopy that we propose. So what is the take-home message? And all of you know that Raman spectrum is linked with the fact that vibrational mode modulates the real part of dielectric constant, which is governing propagation of light in a medium. But it also has an imaginary part, which is frequency-dependent conductivity. And what we show is the off-diagonal part of conductivity, which is linked to the Berry curvature dipole, can be exploited to measure vibrational frequencies. And that's the spectroscopic technique that we have proposed using this analysis. Okay, what about experiments? And this is where Manda's group came back in. And unfortunately, they couldn't do exactly what we wanted them to do. So what he proposed is, instead of looking at natural vibrations of a lattice, he induced driven vibrations, meaning this is the geometry. You have bilayer graphene, and these are the transverse electrode measurements, and this is where the electric current is flowing along x direction. And this is a driven vibration, so vibrational frequencies are very low, easy to measure in a circuit structure, okay? So indeed, what he was able to show along with his students, Surat, is basically the prediction we have is more or less verified in terms of dependence, quadratic dependence on applied field, as well as linear dependence on the frequency. But this interaction with experiment was very rich because it also told us that our theory missed certain peaks that they found. And those peaks were linked with the fact that graphene also can have pseudo-electric fields. And that allows, so basically the physical picture is shown here, that you have, these are the graphene bands, and these bands with the non-trivial Berry curvature can tilt, and that gives rise to Berry curvature effects. Whereas if the distance between the two Dirac points oscillates due to the strain mode, that gives rise to pseudo-electric field. And what the experiment showed is basically you can have both of these effects in the twisted bilayer sample. And as a result, we show that both pseudo fields as well as geometry emergent fields can couple with each other and give rise to very interesting phenomena. I'll summarize my results. We introduced a new experimental technique we call GQS vibrational spectroscopy in both transport and emission modes, which combines the capabilities of infrared, Raman, and Brillouin spectroscopies. It could be generalized to other dynamical excitations. And the geometry ideas are applicable to much wider set of systems. It was much easier to show among the wonder materials that Andre talked about, but they will have much richer consequences in 3D. And indeed, we have a partial experimental verification, which is linked to the driven vibration rather than natural vibration of the lattice. So I'll thank my collaborators, Bhuvaneshwari, Mandas, and his group. And also, we were joined by Amit Agarwal from IIT Kanpur to explain the pseudo fields effect as well along with this. And thank you for your attention.